All aboard.
All right.
Got it.
Got it.
Got it.
Okay.
Hey, people out there can see us now.
Yeah. Boy.
So where's Curtis?
He was here.
He'll be here.
I saw his window come up.
Well, you know,
Called
Curtis.
me a while ago, said he'd be here.
Well, we got 43 people, 44.
There he is
There you go.
Boy.
with a blank panel. There we go.
There he is.
There he is.
Boy.
Okay, we see you, Curtis.
That's not your home in Wrightwood, is it?
I don't know. I can't see the. Might be.
Okay, guys.
Oh,
Oh boy.
oh, looks like Jose's parked out at Griffith Observatory.
Oh yeah, I'm looking over.
Can you guys hear me?
Kind of cold out here.
Yes.
Can you hear me?
Yes.
Yes. Yes.
Yeah, I
But
hear
don't
you.
not hear?
And-
No.
Can't see you, but we can hear you.
We did see you 10 seconds ago, but now you're. I don't have an image for you, Curtis.
Yeah, when he came on, he was frozen too, I think, for a while.
I don't think we
Oh,
have
really?
Curtis again.
Oh, okay.
He's probably Lancaster and has an even worse internet connection than I do.
You guys got to get off those DSL modems. I'm telling you.
I can't. There's no option out here.
In Duarte,
Yeah, no other options. They
No
don't
fiber
even
optic.
have
no cable.
no cable. Well, they have cable. I can get that, I suppose. They don't
There's
have any
Starlink.
fiber optics, though.
Time for a Starlink dish, Tim.
I was gonna say.
Yeah.
He only needs it for these meetings. So once a month, even I wouldn't justify it for that.
Did we lose Curtis again? Or?
Yeah.
Well,
think
his,
so.
his panel
in and
came
out.
up, but
There he is. I just saw. He's there somewhere. I see.
Back again.
Okay. Can you
This is-
guys
there he
hear
is.
me now?
he's like,
Yeah. You're breaking
You're-
up, Curtis.
You're
Yeah,
falling into a
your
black
internet's
hole.
not-
Can you guys hear me now?
There you go.
We can hear you.
I-
You got a bad connection.
Can you hear?
no, you just cut out, Curtis.
Curtis,
Let me,
Kill your
Huh?
video. Kill your video. That might help preserve bandwidth.
Yeah.
yeah, let me try that. That's that. Can you hear
Oh, that's a
me now?
lot better.
Okay, I'll just go ahead and do it without the video. Okay, this is as long as you guys can hear me. This is the November 2021 general meeting for Los Angeles Astronomical Society. I will officially pound the meeting into order at 8:05 p.m. Okay, first thing on the agenda for the meeting is we will go ahead and of course, for any questions during the meeting or any comments, use the chat room to be able to make comments and questions. Of course, everybody will be muted for the Spencer will the link for the all-important door prize registration for the door prizes. So that's the first thing we need to do. Okay, first thing I will ask, do we have any new members on board tonight?
Looks like
Speak up,
no.
people.
Anybody?
And we only had 4 new members this month.
Do we
Guess
have new
not.
members?
I guess not.
Well, is anybody online here? Any of the new members online?
Nope.
Do we have do we have any visitors online?
Got Steve.
I've visited before, but sure, I'm a
Okay.
visitor.
Okay, so the announcements that we have, of course, we got a speaker for tonight. The guest speaker, Steve Levin, but beforehand, we're going to talk about, we have the nominations for the board and the officers tonight. We also have the, Well, I'm going to let Tim mention this one about Griffith Observatory and talk
Oh.
about Garvey Ranch. Exactly. I don't know what I should say on that tonight on Griffith Observatory right now, but Tim, whatever you think we need to discuss on the event going on possibly this weekend.
Okay, Griffith Observatory has decided to hold a stealth, non-announced, don't tell anybody, sort of almost public star party. And
Thank God
Well,
this
they-
is being recorded.
they have room for 6 of our people to go and set up telescopes, and they'll give you parking in the employee area or something, not in the regular parking lot as you normally would. And Giovanni will be there to help you, get stuff to. And so, but we can only deal with as many as 6. And so it's a small number. And it's not like it's not announced, and nobody's supposed to know in advance. Keep it to yourself. But tell me, and you should be able to find me. It's not that hard. If you want to go, and I'll make the arrangements with Mark Pine to take care of that.
Okay,
And
Phil,
so-
Tim, Phil and myself will be there in my car, one car, just so you know.
Okay.
Tim,
Okay.
why? Do we know why?
Do we know why it's stealthy?
Yeah, and what it's for.
It's stealthy because it's an experiment. They are quite simply scared of having lots of people all over the place. That's not what anybody told me, but I'm sure that's what happened. So they're going to look and see how it goes, and then decide whether or not they want to try it again next month. So we're guinea pigs in an experiment. They have plenty of people on their lawn anyway without attracting attention, and so and so they just want to set up some telescopes and see what happens, and is there a disaster, and if not, they'll maybe they'll think. So you work there, ask Mark Pine. I don't know.
Well, I do know when I've worked there at night that there are almost 3 scopes out there, not counting the Zeiss, when things are going okay. And sometimes they have less than that because somebody calls in sick or can't make it or something like that. So I'm not sure what's going on, and I won't be in until that Saturday, which is why I am not volunteering, because my shift ends at 4. I got to get off the hill and actually eat my first decent meal of the day. And so by the time I get back, it's probably going to be 7. So I just did the math and said, you know what? This isn't going to work for me.
Okay.
So I
Tim,
will not be there.
Tim, there's a
That-
question in the chat, the date, and I put down the November 13th. Can you confirm that?
Yeah.
It's Saturday.
Yeah.
I think so. Is that the 13th or 14th?
That's
No.
It's this Saturday. That is correct.
Yeah.
Oh,
Whatever
so
that.
it is
No.
next week.
Yeah, it's this Saturday, whatever that is.
You know what?
13.
I would actually be happy to volunteer for that. I don't normally tear my scope down, but I really miss the star parties.
Okay.
No, the reason I said it, because I'm not a visual guy. In other words, when people come to look at my setup, they don't get to see something through the scope. They get to look at a laptop that is streaming what I'm shooting. And in that case, it would be SharpCat.
Well, that's all right. That's what Dave always does. So
Yeah, so you'll take
Oh,
over
Okay,
for
well,
me.
anyway,
Sorry,
well,
sorry, Curtis, I couldn't hear you.
let's get back to the can you hear me?
You're breaking up again, Curtis.
Did the
yeah, bad
audio
connection.
turn off again?
Voice is breaking up. Bad connection.
Let me try something else. Let me try something else. I'll
Just
be
talk-
back
just-
on
Curtis, just talk slowly. Curtis, if you talk slowly, it should be okay.
minutes, okay?
right.
Yeah.
Use your phone, Curtis. Probably better than your internet.
Yeah.
Would be.
It
Guys,
would be.
Probably.
Oh,
Well,
yeah, I'll try that. And when the speaker's on, I will go into, the internet's flaky
mode.
here.
yeah.
Yeah. Okay.
Curtis,
Zoom will let you
But now
connect by
you guys
telephone, you know.
are seeing the reason why I was hesitant on announcing the Griffith Observatory this weekend. Yes.
So enough.
Yeah,
of that.
let me try that, see if I can do that. Okay, let me try something else.
Okay.
Can we
And
move on without you?
I will be silent for a little bit then. Spencer, take over for the committee reports.
Okay, committee reports. Let's see.
So clear.
John, you want to give anything on Lockwood?
No, not really. There's not much to talk about. We're getting kind of into the season, cold weather coming up, so we haven't done any work up there, mainly because of COVID this year. Hopefully in January, we'll start having committee meetings again and do some planning for starting work up there. We got quite a bit of maintenance to keep up with and some projects to work on, but I think this year we're pretty much done.
Okay.
Yeah, John, Kevin Gilchrist here. I did go up, and I met five new people who I had never met before.
Kevin.
Kevin, you've got
Kevin?
two audio feeds coming in.
Oh,
Yeah,
I do.
and you're
Oh,
distorting.
hold on.
Turn off one of them, Kevin.
Wait a minute. Mute.
Come on,
How's
everybody,
that?
get your Zoom
Okay.
chops together.
All right, there we
Okay,
go. Well, I
better.
started on one device and trying to move to the other, and it didn't take.
I
So
have to say, people.
we all
that-
need to be like David and stick a freaking studio quality microphone right in front of our screen.
Okay.
Okay, you guys.
so
can you
anyway,
hear me
we
now?
had
Do you
I think
have
so.
me now? Are
Yes,
you
we
able
have
to
you.
hear me?
Yes. Go
You
ahead.
sound
Kevin.
good.
Go ahead,
Are
Curtis.
you able to hear me now?
Yes,
Yes.
go ahead, Curtis. Yes, go
Okay,
ahead.
now we can go on. How
Kevin
far
has
did
the
we get?
floor.
Kevin was
far-
giving a report.
Okay, Kevin, continue on then.
Sure. Met five new people who I'd never run across before. I was either first timers that evening, or maybe they had been there 2 or 3 times prior. And then there were only 3 other people there that I knew, plus me. I didn't stay terribly late because I turned out it was a little underdressed for the temperatures coming later. But it started out as a really beautiful, clear evening, very steady. And everybody that was up there was doing imaging. And that's it.
Cool.
And this was where?
Lockwood.
Lockwood.
Okay.
Okay,
Okay,
sounds good. Thanks a lot, Kevin, for the report. And I think we'll go on from that. Ford Observatory, we're ready to, it's ready to be shut down almost for the winter time because I think the ski area is going to be starting to make snow. They try to get open before before Thanksgiving. I don't know if they're going to make it, but Ford may or may not be. We may be able to do something at Ford. We're not sure at this time. Daryl, I think you're done for the season at Mount Wilson.
Last LAAS session was this past Saturday and turned out to be really excellent. There was a nice, pretty deep marine layer, and we got to see a lot of stuff. It was a really nice night. The seeing was good. We had a bunch of people. Everyone had a great time. Right, Amy?
It was fabulous. It was really an experience.
A lot of
Okay.
first timers. There was probably 80% of the people there were new members or first time people. So it was a really fun night for everyone. We got, Saturn and Jupiter and Neptune, and we stayed. The diehards that stayed late enough got Orion too. So,
Good.
but there was only 5 people left by the time we could get to Orion.
Daryl, you said Neptune. Did you see Triton?
Sure did.
The large moon of Neptune? Great, I'm glad. At least you had a marine layer to block some of the lights from Los Angeles. That sounded like it was a great star party.
No, it's good. We got two galaxies. We got 7331 and M32.
Yep.
Yeah, we went out to, also we had some of our club members went out to the Nightfall in Borrego Springs. And we had a great time out there. And it was actually fairly warm in the evening hours, so it wasn't too bad. Okay, I think we're done with the committee reports. Any other committee reports? I think we're okay on that. Okay, we'll go on to the nominations. This is the time you get a chance to nominate the officers and the board of directors for 2022. I will turn that over to Spencer. I'm not sure exactly how it's being handled, but Spencer, you got the floor.
Okay, hang on a second. So I'll post it in the chat as well. So we're opening up the nominations. So you can either, the rules are that you can nominate somebody, you can either self-nominate or nominate somebody else to be for either the officers, which president, vice president, secretary, treasurer, or for the board. And how many board members do we have? I forget.
We have eight board member openings, yes,
okay,
and one alternate.
Okay, so you can either nominate yourself or somebody for one of those positions. The rules are that person who's being nominated has to have been a member for at least a year. And then, so you can do two things. One is that there's a link right here for the nominations. You can either do that online, or in the past when we've had general meetings in person, people will stand up and nominate somebody. So in lieu of a general meeting in person, you can use a chat to nominate somebody as well. So we'll have the nominations open until Saturday, November 13th. So if you're doing it other than at the meeting tonight via chat, use that form that's on the displayed on the screen. And again, I'll post that in the chat later. Then those who are nominated and want to run have to give me a short bio for the ballots. So just email the bio to me, and then we'll put together a ballot that will be sent out via email. And it's a form that you just fill out electronically. And the cutoff for the voting is December 11th at 11:59 p.m. And we'll announce the results at the Monday, December 13th meeting. And so this is the slate of officers that will then take their positions starting in January.
Hey, Spence, are we still holding to the rule that the president must come from the board?
No,
no,
that's
I don't
never
think
been
that,
a rule.
yeah, that's never been.
Oh,
in
that
the
never
bylaws.
was a rule.
Yeah,
Okay,
no.
I thought it was.
So, any questions?
That means you can run for the president if you want to, Dave.
Right, Dave.
If nominated, I will not run. If elected, I will not serve.
And I was going to say Spencer for president.
Not in a lifetime.
I knew you were
Spencer, where
going
he
to say
is.
that, but I had to do it.
I got
Spencer's
news.
an amazing secretary.
If we didn't have Spencer for secretary, this group would have a lot of problems. I'll tell you.
I know.
Spencer's on it.
Oh, no, you're right. We can't have him as president. Shit.
All right, so I just posted the link for the nomination form there, and we have we have some nominees already. So I've been nominated for secretary, Rafael Gonzalez for board. So those are the two that have come in on the chat, and like I said, I posted the link for electronic nominations. So that's all I had. So actually, one more thing. So when you can send me the bio, a short blurb about yourself and what you're interested in, things like that. And what Andy, our communications person, does is that she and I will compile the bios, and then we'll send those out to people ahead of time, just as probably in a newsletter or something like that, ahead of the voting, and then we'll send it out again with the ballots. So any questions or comments? So okay, Tim nominated himself for the board.
I
Again?
second it. I second that.
All right.
I'll
Okay.
third that one.
All right.
Ugh.
So, okay.
I nominated Curtis for president again.
Okay.
I'll accept that nomination. And
Okay.
I'll nominate Joe Phipps for
All
board
right.
of directors.
Put that, guys, put that in the chat because I'm
Okay.
not going to go back and listen to the audio. Or use the form, either one. Okay. That's all I had to do. All I had to say about nominations.
Okay, then we'll go on. The LAAS Astrophotography contest results. Spencer,
That was quick.
do we have Alicia on the line tonight? Is she on there?
I think
I
I
heard
saw
that.
her. Okay.
That was quick, right?
Oh, she's on here. Okay, because I didn't
I'm
see
here.
her name
What
on
do you mean
there.
I'm not
That's why.
here?
Huh?
Okay.
I didn't
What?
see your name. That's why.
She's on the
Oh.
second page.
It says
Oh.
Stephanie Madison.
Oh, that's my mom's account. Let me check.
Okay, so wonder I couldn't find you on there.
All right. Okay.
You're
So,
hiding. You're
All right.
sneaking.
Awesome. I'm like a ninja.
Okay,
okay.
okay. So should I turn it over to you, Spencer, or Alicia?
Well, she's gonna talk, and I'm gonna drive
There
the
we go.
slides. So
Okay.
So we had 3 categories. So this was the first category, and Alicia, ready to unveil the winner?
Yeah, I'm ready.
Okay.
Okay. So the winner for first place was
Everybody
Brian.
see that?
Yes.
For the Dolphin Head
That
Nebula.
figures.
Yeah, the Dolphin should have won.
Okay. All right,
Yeah,
run-
nobody can resist Flipper.
okay. All
Right?
right. All
That
right,
dates my.
I want to
That
give.
dates me.
I want to first thank everyone for all the entries that were submitted to this contest. I mean, it was a really difficult contest. A lot of people had trouble deciding which one to vote for. And we also want to thank everyone who did go out and vote for this contest. This is going to great cause for LAS. And, Brian did a fantastic job. So kudos to him for winning first place for this category on this. So,
Runner up.
yes. So the runner up is, sorry. Go ahead and say Jay Landis with the Horsehead Nebula.
Nice.
Okay.
Do you tell how many votes they each got?
Pardon?
How many votes each
How
entry
many
got?
votes? Oh,
I don't have the tallies in front of me. Okay. Next slide. The next category is single shots. So this was just so there's so here's the first place.
All right, Lou.
Yeah.
Hey, Lou.
Yeah. So Lou Chilton won with the partial solar eclipse.
Okay.
Should have with that sunspot, the big sunspot right there.
Yeah.
All right.
Jesus.
Okay. Runner up.
Who was that? Oh, of course.
I
And
can't
runner
believe
up was Jed Moon by
Yeah. Yeah.
Oh, you can read, when you blow that up, you can read the name of the, I think it's a FedEx or one of those jets.
Yeah,
All
you
right.
should be able to. You almost can now.
Yeah, I did it.
Okay.
Yeah.
brilliant.
Hell of a heck of a shot.
All right.
I
Next,
voted for that one.
next category.
Oh, what
with
was
the
that?
nice
Oh,
guy
nice.
photography.
Okay.
I gotta go tell my wife that I won.
Of
The
course.
first place
Yeah.
was John Fizzanotti with the Milky Way from Cassiopeia to Scorpius.
Yeah.
No, it's just the
Beautiful.
composition is amazing.
Yeah. Wow.
I mean, it's just amazing.
It's a mosaic of 26 shots. Okay.
Wow.
Wow, that's beautiful.
Yeah,
All
I
right.
should have won hands down because,
Okay.
And the runner up, there was a tie.
oh, of
actually,
course. Oh,
tie. It was between Mike Hayford's Moonrise over DTLA.
yeah, that's a good one too.
And the second runner up was Spencer Suhu with the Aurora Borealis and Big Dipper over Big Iceland. Although Spencer, you spelled Aurora wrong in there. But it's
What?
okay. It's your
Oh,
only your
wow. Okay.
now.
Oops. Spell check. Sorry about that. I'm dyslexic. Okay.
I'm not even going to pronounce that.
Aurora.
Okay. All right. So those are the
So
winners.
the first prize winners and the runner-ups, you can see the winning photos and their names on these website links. And they win a half night of imaging with a 60-inch on Mount Wilson. And we're also going to be compiling a calendar with the 4 top pictures from each category. And I think we're actually going to be giving them a copy of that calendar for the top 4 that are used in each category as well. I think that was the plan. So look out for an email for that. So yeah.
And website merchandise.
Yes, and website merchandise. So look forward to updated website merchandise in the LIS store from the entry photos of the entry photos that were submitted to this contest. It'll be really exciting. Some great stuff being sold there. So go check it out.
Are you going to have that done for the year 2022?
Yeah.
We're going to try.
Okay. I said, because I'm thinking that we're in November already. It's going to be a tight race.
Yeah.
Make a calendar or get?
No, make the calendar.
No, dude. It doesn't take me that long to make a calendar.
Okay.
We're going to have a print on demand type of setup like we do with merchandise on the website. So people will be able to order through the website and get it shipped direct to them directly.
Okay.
Instead of having them all come to one person and trying to distribute them that way.
But that's the old-fashioned way. It was interesting to see what was going to happen.
Whose side are you on here, man?
I'm on the side of mischief and chaos. I thought everybody knew
What are
that.
you, Loki? Oh, you're
normal.
Let's mute him then.
Okay, so right.
Move on.
Okay, let's.
All right, who said that?
Okay, so
Are we?
So I've just reposted the link for the raffle in preparation for our next speaker, because we'll have the raffle right after the speaker. So this is our guest speaker. So Steve has worked at the Jet Propulsion Lab since 1990, and his research interests include the cosmic microwave background, search for extraterrestrial intelligence, measuring magnetic fields in star-forming regions, looking for near-Earth asteroids, and modeling radio emissions from Jupiter's radiation belts. He's done a lot of radio astronomy from large radio telescopes, mountaintop research stations, the South Pole, high-altitude balloons, and spacecraft. He's currently the project scientist for Juno, lead co-I for the Juno Microwave Radiometer, and lead scientist for the Goldstone Apple Valley Radio Telescope Project. He's also an elected member of the Board of Education in Culver City and a frequent speaker on science topics at public venues. Title is Results from Juno, It's a Whole New Jupiter. And rather than me reading the abstract, I'm going to turn it over to you, Steve, so you can take it from here.
Cool. So, and I'm not going to read the abstract either.
I'll stop the share so you can have the screen.
Let me try that. We haven't
Everybody
tested.
else that's not muted, please mute.
Working. So let's try sharing the screen and put it in presenter view and see if you guys can see. Does that look right?
Yes.
Perfect.
Okay. So I'm not going to read the abstract either. I will try to make, oh, it's changing slides without me telling it to. I will try to make this talk pretty quick because I want to spend as much time as we can on questions. But I need to go over at least a bit of an overview of the mission, and then I'll tell you about some of my favorite results. We have way too many results to tell you everything. In fact, even this slide where I started putting magazine covers when we're on the cover of a scientific journal or a popular magazine, I put it on this slide. I'm running out of room. Anyway, Juno is the first solar-powered mission to Jupiter. We have a bunch of science instruments that I'll tell you a little bit about. It's a spinning polar orbiter. So what that means is we go over the poles of Jupiter rather than around at the equator. And the orbit we're in comes very close to the planet, and then spends a long time, initially 53 days in each orbit, far away from Jupiter, and then 53 days later comes by and does it again. So it's sort of like a flyby every 53 days, but that allows us to get really close to Jupiter. And because we're in a polar orbit and the planet's spinning every 10 hours, it lets us choose our longitude. So it took us 5 years to get there, but we got there 4th of July, 2016. We went into a 53-day polar orbit. The plan was actually to reduce that to a smaller, faster orbit, but there was a problem with the main engine. And so we were looking at, well, what happens if we just don't use the main engine again? And the answer was, in fact, the science is at least as good, maybe even better. It just takes longer. So we went to NASA and said, we don't want to use the main engine again because we're not 100% sure it's safe. And look, we can do all the same science. You just got to keep the mission going for 5 years instead of a year and a half. And they bought into that. So that's what we did. We just finished prime mission back end of August. Last science Perijove prime mission was July 21st. And we've started an extended mission, which I'll tell you a little bit about at the end of this talk. But mainly I'm going to talk about science results from prime mission, unless you ask me questions about other stuff. And I also want to mention that this is a principal investigator mission. I think that's actually important. NASA has two different ways that they do spacecraft. They have the really big spacecraft essentially run by a committee, and they have smaller projects run by a principal investigator. So principal investigator, basically you propose to do something with a team put together before your proposal is accepted. So you write the proposal together. And then if NASA approves it, the principal investigator, the PI, is in charge of everything and delegates the authority to everybody else. So it's a lot more efficient. But of course, it also means that you've got, a smaller number of people to do things, and you're cost competitive and all of that in proposing. So this was at the time the largest PI-led mission NASA had ever done. And I think that worked spectacularly well. We've gotten a ton of great science, and we did it really efficiently. And they really got a good bargain. So I like to point that out every time. And Scott Bolton at Southwest Research Institute is the PI. And it also helps, of course, a lot that he knows what he's doing. Okay, so why did we go to Jupiter with Juno? There are lots and lots of good reasons, but the four big ones, the four main things we were trying to accomplish, are to understand the origin of Jupiter by looking at the composition and of the planet, and how it's built on the inside tells us about how it formed. And that's really important because in our solar system, 99 point something, almost 99.9% of the mass in the solar system is the sun. But of what's left over from the sun, more than 2/3 is Jupiter. And Jupiter formed first. So if you want to understand how did the solar system form, how did the planets form, how did we get here, you have to think of it as we're formed from the leftovers of Jupiter. You really need to understand how Jupiter formed. But from the Earth, even though we've been studying it for hundreds of years, mostly what we see are those clouds at the top of the atmosphere. And we didn't know that much about Jupiter until Juno got there and taught us about what's underneath the clouds. So we sent this spacecraft. Well, a lot of what we had in mind was how to see through the clouds one way or the other and learn about the interior. So of course, I mentioned origin, just got to interior. What's the interior structure? How does stuff move inside? Where do the magnetic fields come from? And how are they generated, and what do they look like? Then it's a gas giant. So there's a lot of atmosphere to study. And we wanted to look at the atmospheric dynamics and all the stuff that we can see below the clouds with our instruments. And then finally, in this polar orbit, if you see the magnetic field drawn on that picture, we're in a perfect orbit to study the magnetosphere. So we wanted to look at the aurora from high energy particles streaming down those magnetic field lines. And by crossing all the field lines, we can study things on their way to and from Jupiter along field lines that stretch all the way out very far from the planet, all the way down to very close to the planet. So I won't list through all of the different instruments. I have it sort of color coded by what we had in mind for what those instruments could do, but everybody can do a little of everything for the most part. And I also wanted to point out what I like to say before we launched was we're either braver or stupider than everybody else. Because if you look at that picture, that orange in the picture that's fluctuating and everything, that represents radiation belts. Jupiter is surrounded by high energy particles trapped in its magnetic field that can destroy the electronics on the spacecraft. And there have been previous missions to Jupiter and flybys of Jupiter. And what they've done is basically stayed far away from Jupiter outside those radiation belts so they won't get fried. But we didn't have that option. We wanted to study the planet itself up close so we can see beneath the clouds. So what we did is we said, well, we're going to come over the pole of Jupiter where there's a lot less radiation, dive down in between the planet and the radiation belts and out the other side in a short time so we don't get fried too badly, and then spend a long time away from Jupiter, recovering, sending the data back to Earth and all of that before we do it again. So that was in some ways a gamble, although I think we had pretty good reason to believe we understood the radiation belts, but it was partly my work, so I may be biased. However, it paid off. The spacecraft has done really well, and we've flown really close to Jupiter. So why don't I tell you a little bit about what we learned. So the very first thing I want to say that we learned is humility. Before Juno got to Jupiter, there were lots of ideas about what Jupiter looked like and how it worked. And we were doing a bunch of different measurements that had never been done before. We were going over the poles close up for the first time ever. We were using radio waves to see through the clouds and look into the interior by hundreds of kilometers. We were measuring the gravity close up, which comes from the whole planet, so we'd learn about the interior. We were measuring the magnetic field close up and making a detailed map, which teaches us about the region inside the planet where the magnetic field is generated. Every one of those new measurements, and just about everything else we did that hadn't been done before, gave us a surprise. Jupiter didn't look like what we expected. In fact, after our very first perijove pass, one of our scientists, Mike Jansen, coined a phrase that I really like. We were talking about what the heck are we seeing with all this new data? And he said, you just better get used to it. It's a whole new Jupiter. So what I'm going to tell you about in the rest of this talk, namely, is a whole new Jupiter. Here's what we learned that we didn't know. And I've picked out a few of the surprises. These are nowhere near everything we learned or all the surprises. You can argue over different people have different ideas about which were the biggest ones and the most interesting ones. But anyhow, these are the ones I picked. The deep atmosphere of Jupiter is not well mixed. It's a gas giant. 300 times the mass of the Earth, more than 1,000 times the volume, almost entirely made of hydrogen and helium, right? You'd expect it's gaseous, or even down at the pressures down in the interior, liquid. It should be pretty well mixed. It's rotating every 10 hours. Up at the top, sure, there's clouds. There's places where things condense as it gets cold at the top of the atmosphere. There's sunlight, however weak it is, 5 times further away from the sun than the Earth is. But by the time you get down into it, say 20, 30, 40 kilometers, 100 kilometers into the planet, you expect things to start looking well mixed. If I think of it in terms of pressure, the pressure at which water condenses out of Jupiter's hot atmosphere is at about 20 bars. So 20 times the pressure here on the Earth. So everybody expected you get down below about 20 bars, everything should be well mixed. You're below the clouds. It's way too deep for any sunlight to penetrate. You should be below the weather. It's kind of like getting below the surface of the ocean. You should find things look fairly uniform. We had, in fact, in the 90s, dropped a probe into Jupiter in one spot to go deep enough to below that to measure everything that we could to get to the well-mixed region. And what we found from that probe was, even when it got all the way down to 22 bars, it was still, things were still changing. It hadn't reached some kind of equilibrium. So we kind of thought we just missed it. And NASA was looking for another mission to Jupiter with multiple probes. So we try a few spots. And we proposed instead, no probes at all. We're going to use microwave radiometers. We can see way below 20 bars. We'll look at down to 100 bars and we can cover most of the planet. We won't have to worry about whether it's well mixed. Well, that was totally wrong. We can see everything and measure everything that we said we were going to measure, but as deep as we can look, below at least 100 bars, Jupiter is still not well mixed. There's all kinds of structure in the atmosphere. We're going to talk about that a little bit. We flew over the poles and got good pictures for the first time, and we see polar cyclones in a pattern. There's a octagon of cyclones around a central cyclone in the north, and there's a pentagon of cyclones around a central cyclone in the south, and they've been that way for 5 years pretty much. So we think it's pretty stable. Nobody had any idea it would look like that. The color isn't even the same. Instead of those orange and white stripes, it's a lot bluer in the north and south of Jupiter. Another big surprise. The dense core, we thought there'd be a core somewhere between 3 and maybe 20 times the mass of the Earth, way down in the center of Jupiter. And we in fact found a core, but it's extended. It extends out to perhaps half the radius of the planet. It's dilute and fuzzy. Another big surprise. The belts and zones, the zonal jets that we see, penetrate to 3,000 kilometers in depth on Jupiter. Most people, there were people who argued for that, but most people thought they would be shallower than that. Another surprise. We see a magnetic field that's complex, asymmetric, and sheared by deep jets. We see changes in the magnetic field. The magnetic field is much more complex than expected. And we're still working on understanding what it means. We've seen shallow lightning up near the top of the clouds, which has helped support a theory we came up with, a conjecture at least, to explain some of what we see in the deep atmosphere that has to do with what we call mush balls of ammonia water liquid that flies up like hail up and down in the atmosphere all the way up above the water clouds. So I'll talk about that a little bit too. So those are half a dozen of the more interesting surprises. And let's start with the last one. Let's start with mush balls, because it's just such a cool, complicated, messy kind of thing. So if you look at this picture on the left, and for a moment, ignore all the lines and drawing and words, and just look at the colors, what you're seeing is a measure of the opacity, how well the microwaves can see into the planet. The planet is hotter on the inside than the outside because it's still cooling off from its heat of formation 4.5 billion years after it formed. And the microwave radiometer, things glow in the radio waves depending on their temperature. Hotter things glow more. The microwave radiometer has 6 different channels. It sees into the atmosphere, and how deep it can see depends on each channel and depends on what's in the atmosphere. So to try and disentangle that, there's lots of things you can do, but what we did initially is the simplest thing. Ammonia is what absorbs the microwaves the best out of Jupiter's atmosphere. So we said, let's suppose essentially all of the absorption is coming from ammonia, and we'll take a fairly straightforward model of the temperature of Jupiter's atmosphere and ask, what do you get? And what we expected before we ever got there was, if you did that, you get something that looks kind of like that more or less uniform yellow stripe in the middle of this plot. So look at the figure on the left, latitude 0, so right around the equator. That color coding there tells you how much ammonia there is. And we kind of expected the ammonia to be fairly uniform right up until you get to where the ammonia cloud forms at only a couple bar or less. But instead, most of the planet doesn't look like that. You do see ammonia up at the top, but then there's a deficit in the middle at pressures that get deep. The water cloud is only at about 8 bars, and we're seeing ammonia missing all the way down to 20, maybe 30 or 40 bars, maybe even 50 bars. And then more ammonia coming back as you get deeper. And then that's about as deep as we can reliably see. But there's still more complexity because Not only does the equator have that narrow region, which, by the way, notice carefully, it's a little asymmetric. It's not quite exactly at the equator, but a little north of that, there's a region where that missing ammonia goes even deeper, where sort of an ammonia desert. Now, there's room for some fluctuation here. Maybe not all of it's ammonia. Maybe there's some water. Maybe some of this is due to temperature. But this is very clearly a much more complex, structured atmosphere than we expected. And the first thing we started looking at then is, how the heck do you explain that? What's driving stuff to happen so deep? And why does it look different at different latitudes? Well, we came up with, a few of our folks came up with, a partial explanation, at least, with this idea that we started calling mush balls. The idea of a mush ball is, if you think of hail here on the Earth, what happens is you get drops of water that freeze, and in an updraft get carried up to where they freeze and then fall back down, pick up some more water on the outside, and then get carried up again. And they get bigger and bigger until finally they're too heavy and they fall all the way down. Well, on Jupiter, there's water, but there's also ammonia. So you can get ammonia dissolved in the water. Basically, think of it as Windex with a water ice shell around it on the outside, if you do it right. And the water doesn't melt quite as, doesn't freeze quite as easily because the ammonia is acting like antifreeze. These things can get quite big. They can carry a bunch of ammonia. So this model kind of explains the possibility of what's going on here. If you have these updrafts and you carry mush balls like this, mushy on the inside with ammonia and water and frozen water on the outside, you carry them back and forth and let them freeze. Well, they're holding the ammonia, they're hiding it in a way you can't see, and they might be making that intermediate layer. So this theory sounded, a little out there, pretty hard to convince yourself of, but it started to make sense. And then we got additional evidence that starts to fit together. We see lightning in a way that matches this model. If I look on the right-hand side now, the plot with colors to show sort of a prediction of what that ammonia might look like, that's not too bad not too different from what I see on the left. I probably shouldn't go through unless somebody asks me questions later what all the arrows and stuff but think of wind and convection and how it drives things up and down. To make a model like this, you have to do more than wave your hands. You have to do a little bit of math, and some of that work's been done. And then we got a bit of confirmation for this speculation, because not too long after we came out with this thing, and Tristan Guillot and a few other people were fleshing out the model and seeing that it kind of sort of works, one of its predictions would be that you're carrying these mush balls much higher than the water cloud. So you should see the effects of having something similar to hail at a height much higher in the atmosphere than the top of the water clouds. And sure enough, we found a few examples of small lightning flashes that we see that must be from storms that are therefore are shallow, much higher in the atmosphere than where the water cloud is. If they were down at the level of the water cloud, you wouldn't be able to see small lightning flashes because they'd scatter and they'd spread out and they'd look like bigger flashes, or they'd be too dim to see at all. But we see some of these, so that tells us, yes, something is causing lightning, and to make lightning, you need hail. You need 3 phases of water, at least for the kinds of lightning that we think exist on Jupiter and the lightning that we see on the Earth. Generally speaking, you need liquid and solid and gaseous water all to coexist in the same place, and mush balls predict that, and very few other things do. So it's looking pretty promising that maybe this mush ball thing is actually right, and that's one of the big things we've learned from Jupiter, from Juno, about how complicated Jupiter's atmosphere is. On top of that, more complications for the atmosphere. Our microwave radiometer, remember, we see through the clouds, we see things at depth. And what we found is vortices, storms. Jupiter is covered with storms. Everybody pretty much knew that. You can see that from the Earth. We see a lot more storms in the north and south than people knew for sure were there, but that part wasn't a huge surprise. But if you think about storms, that's weather, right? You expect the weather to happen where the clouds are and above. You don't expect a whole lot of weather way down deep below the clouds. There's no ground to interact with. There's nothing obvious to generate all that circulation and make things move around and convect and so forth. On the Earth, you get big storms like hurricanes. You get them where you have hot land and cold water, or vice versa, or you have cold air coming over a warm surface, right? Well, you don't have any surfaces at Jupiter. The only things that we thought you could act like that surface would be the cloud layers, but way down below the clouds, as deep as we can see, we see some of these storms all the way down at 200 or 300 kilometers into the planet, maybe even as far as 300 or 400 kilometers. 200 bar, 200 times the pressure here on the Earth. So that's pretty impressive, and still leaves us with a puzzle. Maybe we can connect that up to the mush ball thing, but it's pretty deep even for the mush balls. More about the atmosphere. One of the things I mentioned was we flew over the poles and we got this big surprise. We actually discovered this first with the visible light camera, Juno cam, and remind me at the end to talk about Juno cam a little more. But it's in many ways easiest to see with the infrared camera. So here's a couple pictures of the north and south pole of Jupiter as seen in the infrared. So here on the left, you can see this big cyclone at the pole, surrounded by a pattern of 8 cyclones, and it stays in that fixed pattern, and it slowly rotates around as these cyclones just jiggle a little bit, making circuits around the pole of Jupiter over and over during the mission. Now, the way our orbit has worked, the infrared camera gets a better view of the South Pole. So I'll show you a movie that the JIRM team made with various images from successive perijoves. What you'll see is those cyclones stay in the pattern, they circle around, they jiggle a little bit, and then at some point, another cyclone squeezes its way in, and you have 6 of them for a little while before it gets rejected and settles down on the same pattern of 5 cyclones again. So explaining how this works, why the cyclones last so long, why they make these crystalline-like patterns, has been another puzzle for Juno to try to figure out. And we've made some progress. People on the team have concluded that actually these cyclones have some counter-rotating anticyclonic motion on the outside. So think of them as spinning one direction on most of the cyclone and then kind of a ring spinning the opposite direction on the outside. And that helps to keep the cyclones from interacting, from eating each other, and instead makes them push apart, including the central one pushing them apart. And then we already knew that on a rotating planet, storms tend to drift north or south, depending on which direction they're spinning. So you see that on the Earth with hurricanes, making their way up the coast, the east coast of the US, for example. And here at Jupiter, you expect cyclones to drift north, and in the south, cyclones drift south. So you get them piling up at the poles, sort of fitting where they can. And then the size of these things matches up reasonably well with how many. These cyclones in the south are a little bit bigger than the ones in the north, and you can fit 5 around rather than 8. And that's a stable configuration. Saturn, which has, where we see cyclones that are a different size, and Saturn wouldn't work to make this number of cyclones in a little crystalline structure like this. Jupiter's sort of the right fit, given how fast it rotates and what the atmosphere is like and the size of those cyclones. We still don't have a good explanation for why they're this size and why they're a little different size in the south than they are in the north. If I move on a bit and talk about the dense core in the middle. So as I said, our gravity experiment found this diluted, fuzzy kind of core. So to give you an idea of how we get there, remember our spacecraft is falling past the planet every 53 days. We've shortened the orbit now and extended mission. It's every 43 days now. But either way, for an hour or two, it falls very close to Jupiter and flies on by. So if you can see my arrow here, move close to the planet and fly by the other side, right? So as it does that, as it falls close to the planet, gravity is what's making it do that. It's going to speed up and slow down as it goes past. And if you think about this giant ball of fluid, 318 times the mass of the Earth, and rotating every 10 hours, more than twice as fast as the Earth, it's clearly going to bulge out at the equator. But if it's got a density profile to it, if it's got a dense core down in the middle, that's not going to bulge out the same way as it would if it didn't have a dense core, or if it wasn't as dense, or if it was bigger or smaller. So that means as the spacecraft falls past the planet, the way it speeds up and slows down is affected by the gravity from the entire planet, including that core. So we can fit the very, very precise measurements of how fast the spacecraft is moving to the predictions of what gravity should do to it, depending on whether there's a core or not, and get a measure of what's going on way down deep where we can't see. That result really puzzled everybody, a big surprise again, because we got a core that's about the right mass we expected, but it's spread out over half the radius of the planet. So the first question is, how the heck did that happen? And the straight up answer is nobody really knows. And the next thing is, okay, if it's spread up like that, then the composition has to be much different from what we thought, right? The heavy stuff should have fallen to the center to make this core, but if it didn't fall all the way to the center, then that means some of the heavier elements are spread out throughout the planet in this fuzzy way and maybe differentiated and so forth. So we have to try and figure out what that does to our models of how Jupiter formed. Lots of different concepts being worked. The one shown in the picture is the idea basically that something big smacked into Jupiter while it was still forming. In some ways, that's kind of an easy out, right? We got, it's really stirred up. We don't understand how. Well, just hit it with something. It might very well be true, but we're still working on trying to either establish that it is, or that something else happened to cause that. There's other models for how Jupiter formed, but this is a big part now of trying to figure out how did Jupiter form and how did our solar system form, because now we need to understand that deep core. And we also are still looking with our extended mission to see if just maybe there might be an even denser differentiated part of it, a denser core way down in the center of the planet. No evidence for that yet, but stay tuned. Okay, then another piece is these zonal jets that I mentioned that penetrate to 3,000 kilometers. They shear the magnetic field of Jupiter. So if I look here on the left, remember, we talked about measuring the magnetic field to learn about the interior. And if you think about the magnetic field here on the Earth, it's basically a dipole. But the way magnetic fields work is the further away you are from the magnet, the less you can see the complicated parts of the magnetic field, and the more you can only see the simplest part of it, which is the dipole. Well, on Jupiter, the magnetic field, before we got there, we thought, well, it's generated by this ocean of liquid metallic hydrogen down in the center. So think of hydrogen gas, right? The lightest element there is. But on Jupiter, the planet is so massive, the pressure is so high, the conditions are so intense that not only do you squeeze hydrogen down and turn it into a liquid, but you squeeze the electrons right off the atoms. It conducts electricity, it's a metal. And it's the swirling motions of that liquid metallic hydrogen that generate most of the magnetic field. We thought before we got there, all of the magnetic field. But that's down in the interior of the planet. And even though we're flying really close to the planet, we shouldn't be flying so close to that dynamo region that we can see the level of complexity we see in this magnetic field. If you look at the little movie that's running in the upper left, what you see is a map of the magnetic field lines and color coding to give you something about the intensity at the surface. Look at that North Pole. It's not a North Polar magnetic field. It's like 10 different North Polar magnetic fields and hot spots and cold spots. And then there's the great blue spot, we're calling it, right near the equator. There's a spot where the magnetic field is again concentrated with the opposite sign. And then the southern hemisphere, magnetic field actually looks fairly smooth and dipolar, kind of like you might have expected. So it's highly asymmetric, very complex, doesn't look like just an ordinary dipole. And that indicates at least part of the magnetic field must be generated or affected by something closer to the surface, closer to where we're measuring, in order for that complexity to make its way out of the planet. So one of the things our team did, Kimmy Moore got a bright idea for a way to look at variation in Jupiter's magnetic field. So she got measurements that had been done a long time ago of Jupiter's magnetic field with previous spacecraft, nowhere near as precise as ours, but there's this big, long 30-year time span, and we have very precise measurements. And by combining those together, you can actually take a look at how the magnetic field has changed in that time. You can also, if you look at the map on the right, look at the shape of the magnetic field we see right now and compare it to the zonal winds. The combination showed, yes, the magnetic field has changed in the last 30 years. And the way it's changed is consistent with it being blown around by the winds of Jupiter. So those zonal winds, the belts and zones that we see shown in the lower left in the little movie that shows how deep they go, they have about 1% of Jupiter's mass in them, about 3 Earth masses. But the key is right about the bottom of that 3,000 kilometers or so is where, under those conditions, really high pressure, hydrogen gas should conduct electricity a little bit. Nothing like the magnetic dynamo way down in the interior where we have liquid metallic hydrogen conducting electricity really well, but conducting electricity at about the level of, say, salt water. So it's really interesting that the winds stop around there or fade away, and that we can see the magnetic features sheared by something that looks like the winds. So the plot on the right is showing the wind speeds on the surface superimposed on a magnetic field map. And you can see that that great blue spot, which is right near the equator where the winds are fastest, actually looks like it's been distorted by the winds. So now we can kind of put together a story that starts to make sense, that says, well, maybe the reason those belts and zones, those zonal winds, only go to 3,000 kilometers and don't go even deeper into the planet is that that's where they're getting resistance from the magnetic field. And the reason the magnetic field is a little bit distorted is that the winds at that depth of a few thousand kilometers are pushing it around. And the combination kind of holds together and makes another interesting story that seems to match the picture of what we've seen. Okay, so I've told you about half a dozen or so surprises and things we've learned. I want you to remember those and be ready to ask me questions about those and other things when we get to that part. But first, I also want to tell you a little bit about Juno's extended mission. So if you look at this picture, this is a little piece of our orbit for a few different orbits. And let's start with the gray one that says PJ1. So for that orbit, our closest approach to Jupiter, Perigove, was just 4 degrees north of the equator. That's how we started. So that was the general plan, keeps you out of the radiation belts, lets you get really close to the planet in what we thought would be the most interesting part, the equator. And you fly by, you measure the magnetic field, the gravity, radio waves, all the stuff we were talking about with the spacecraft spinning more or less like a wheel rolling across the planet. So you can measure with all those radio waves. The radio receiver with its 6 different channels can look at any given spot on the planet multiple times from a bunch of different angles. It's called limb darkening. It's another way of doing the measurement. Well, that's where we started. But Jupiter's not a perfect sphere. So an orbit around Jupiter doesn't stay oriented like that. What's called the line of Absidies, the long part of the orbit, rotates a bit because Jupiter's bulging out at the equator. So by the end of our prime mission, Perigove 34, a few months ago, you get the blue line, where now our Perigove, our closest approach to Jupiter, has moved north. And if you look at the North Pole, we are quite a bit closer to the North Pole than we were with that first orbit. But in our extended mission, which NASA has approved, if the spacecraft survives, eventually by Perigove 75, which is about when we'd run out of fuel, that Perigove is at 63 degrees north. And now we're really close to the North Pole. So we're on a journey to explore the unexplored north of Jupiter with our extended mission. One of the key things we're going to get to do is all the cool stuff we were able to do down near the equator. We can try doing all of that way up north and in those unexplored regions that are completely different from what we see at the equator. From here on the Earth, you can't see it. This picture is taken from the side, but remember those pictures from Juno that I showed you a little while ago. The North Pole looks totally different from these belts and zones at the equator. So there's reason to think the atmosphere might be a lot different. And of course, that's also the region where the magnetic field was crazy complicated. So it's a good place to learn stuff as well. So that's the basis of Juno's extended mission. But there's also another key thing because the orbit is changing. If you start with our first orbit, now it's at the upper right of this picture, where it says inbound to Perigove 1. So we had this big long orbit, spent a long time away from Jupiter, come flying in, fly past the planet, and come around the other side. But now I want you to look at, as we're coming in, what that orbit looks like. By the time we rotated around with the Perigove further north, to Perigove 34, our incoming orbit was crossing Jupiter's equator way out here, but that's much closer to Jupiter than it was before. And Perigove 34, we were crossing the equator really close to Ganymede. So the 4 big heavy moons of Jupiter are Callisto, Ganymede, Europa, and Io. And Ganymede is plenty heavy enough to let us change the orbit a bit. And of course, it's really interesting to study bringing along instruments that haven't been brought to a moon like that before, such as our radio receiver that can see the ice now instead of gas and study Ganymede. So we collected flyby data from one good flyby of Ganymede, and we're working on understanding what that means. And we also used Ganymede's gravity to change the orbit to be a little faster, so that instead of being a 53-day orbit, it's a 43-day orbit. And the reason we did that was mostly to get more orbits squeezed in this next period from right about now till a little bit after we go by Europa. And the reason we want to put more orbits in there is that's a sweet spot in the timing for when Jupiter goes around the sun. In the 10 years or so it takes Jupiter to orbit the sun, our orbit around Jupiter itself doesn't change much in its orientation in the plane of the solar system, but Jupiter moves. So instead of orbiting from the side of Jupiter as seen from the inner solar system, like the Earth, after a while, we're orbiting instead perpendicular to that, so away from the Earth and back, and putting Perigove, the part closest to Jupiter, right on the sun side of the planet. Keep on going, you get to these orbits that I said were the sweet spot, where it's once again on the side of the planet, but on the other side. And that's a good orientation for us because it means if the spacecraft is pointing its communications antenna at the Earth, its spin axis is pointing pretty close to the sun. The spin axis has to be pointing at the Earth. The spacecraft is spinning around a line that becomes perpendicular to the orbit again. And we get to see the Earth really well as we spin by, even while we're still communicating with the Earth. So we can do gravity science and all the other remote sensing stuff at kind of the same time. So we like those orbits. We wanted to get more of them to fit in here. Then, of course, we also get to fly by Europa. Europa is really exciting. I'm sure you guys know there's liquid water underneath the surface ice on Europa. We can learn something about the ice on Europa using our microwave radiometer. We can look for plumes, which is kind of a long shot, but maybe we'll get to see something with the cameras. So we're going to do close flybys of Europa, one really close flyby, a few hundred kilometers, and then others that are much further. And we keep on going, collect more data, get further north, take a look at Io, eventually, Perigeo 57, if the spacecraft survives. We'll get really close look at Io, and we can measure the gravity and hope to learn something about the interior of Io. Remember, Io is covered in volcanoes, has tidal heating from Jupiter. There's some really interesting questions about what's going on deep inside it. Keep on going. Maybe by the final orbits, we'll even get to take a look at the rings. And also, remember the orientation I talked about for the orbit. At some point, way late in the mission, the perigove, the pass by Jupiter, is going to start happening on the far side of the planet. So that means it'll go behind Jupiter a little bit as seen from the Earth. So we lose some information because we're out of contact for gravity passes, but we gain some really interesting things because we get to do an occultation. As the spacecraft flies past Jupiter, when it crosses that boundary and the radio signal from the spacecraft is coming through the top of Jupiter's atmosphere for a little brief instant, we can get a measure of what's going on in the atmosphere now with radio waves that are leaving the spacecraft and coming to the Earth, or leaving the Earth and going to the spacecraft. So those radio occultations are really valuable and can teach us something about Jupiter and its atmosphere and its aurora. Okay, lots more stuff I could say, but I want to have time for you guys to ask me questions. So let me stop there, other than to mention, take a look at these websites if you want, or our recent press conference, which is shown in the lower left, and remind you that we have a camera on board, a visible light camera, that's there for people to use. So we collect that data, but we just dump it out on the Mission Juno website, and we let anybody who wants to collect it up and make good images out of it. So if you go to that Mission Juno website, you'll see some spectacular images of Jupiter that are made by amateurs. So if any of you haven't seen that yet, you really ought to go take a look, especially if you're into astrophotography and work on improving your images and stacking images together and stuff like that, because you might get to do that with spacecraft data just by going to the website and playing around. Okay, that ought to be enough to get people to ask me questions.
Well, I'll start. There are some questions in the chat. So do you want to look at the chat, or you want me to read them off to you?
It'll be really helpful if you can read them off.
Okay,
and
so
I'm gonna, I think, stop sharing so that I can see your faces and you can see mine.
Okay.
Let me figure out how to do that for a minute. Here it is, stop share. There we go. And if I need to, I'll bring it up again to show pictures if I need him to answer questions.
all right. So the first question is from Mike Boris. So the ammonia gas and water in the atmosphere sounds like the old refrigeration units, as liquid ammonia vaporizes and absorbs large quantities of water of heat without changing its temperature to some extent. One of the same sort of process applies here.
Yes, but if you think about it, that process has to apply where the temperatures are about right for ammonia to make that phase transition between gas and liquid. And that happens way up at the top of the atmosphere from my perspective. That's at pressures, I don't remember the exact number, but it's in the neighborhood of 1 bar. So it's pressures similar to the pressure here on the Earth. Maybe it's 1.5 or something like that. So all of the deep structure that we see cannot be caused by that. The clouds that we see and the storms and all of that, they might well be influenced by that heat of vaporization of ammonia and the way the heat is carrying from the inside and what ammonia has to do with it. Then if I go deeper, pressures of about 8 bars, so 8 times the Earth's pressure, that's still a tiny, tiny fraction of the way into the planet. But now I get to a pressure where water freezes or melts, right? You go deeper and it's melting, go higher and it's freezing. So that again could have the heat of vaporization of water can do something to the atmosphere and make clouds and storms and weather, right? So that's the picture we had before we got to Jupiter. So the same kind of thing you're talking about with refrigerating, with ammonia in a refrigerator, that heat of vaporization, we thought, well, that's a big part of the storms and things, and that's part of what's going on with Jupiter. But when you get below that, where you don't have anything that can act as a refrigerant, it's not really a refrigerant, but you know what I mean, doesn't have that heat of vaporization, then it should all be well mixed, and it's not. It's just not. So we don't really know exactly what's causing it. This thing with the mush balls is a way of getting that stuff deeper, right? So if that's really what's happening, and it looks like it's kind of fitting pretty well, then maybe that explains down to 20, 30, 40, 50 bars. We're still left trying to figure out how deep that can go, and if we really still need something else to explain the structure that we see that's down to 100 bars, at least in the latitudinal structure, the difference between the equator and other regions. So there's still a lot more to figure out, and I think it just has to go well beyond the concept of the heat of vaporization driving everything. That just isn't good enough to explain what we're seeing.
Okay, next question is, could floating microbial life exist at the 0 to 2 bar level and 0 to 50 C level? Is Juno capable of detecting phosphine and other potential biomarkers?
Wow. Let me start with the answers. I don't know, but give you a little bit more depth to the picture than that. So Jupiter's atmosphere is in fact pretty complicated. It's also pretty damn cold at the top and crazy hot down at the bottom. So that means, yeah, if you look for what's the right temperature regime for some form of weird looking life, there probably is one in there somewhere. On the other hand, it's not going to be carbon-based like us. It's really hard to figure out how that would work because you've flooded the thing with ammonia. It's mostly hydrogen and helium. And the next most abundant thing is oxygen. So that ought to be water, H2O, combine the oxygen with the hydrogen. We don't know how much water is there. It's one of the key things we're still trying to measure. We think we know roughly how much water is at the equator, but the rest of the planet looks so different that there's no guarantee that it's the same amount elsewhere. The amount of carbon doesn't really match up. Some of the stuff should have sunk down to the middle. The energy sources look nothing like here on the Earth. The temperature ranges aren't the same. I mean, somewhere in there's a temperature that matches Earth-like temperatures, but it won't have the same energy sources as we have. So if I try to say, well, what am I going to find there? Could I find life? Sure, I'm not going to rule out some microscopic organism that has chemistry different than ours living on Jupiter. But it's really hard to believe it would look like us in any way. Carbon-based DNA stuff, really hard to picture it surviving on Jupiter itself. Europa's moon, maybe, but Jupiter, it just doesn't seem like a very hospitable place. And then, of course, it's covered with storms and things are swirling up and down. And here on the Earth, life forms live in a fairly narrow range of temperatures, right? If you take, a living organism here and you boil it, you're going to kill it. And if you freeze it, for most of them, you're going to kill it that way. And sure, there are some that live in really hot water and some that live in really cold places, but not much that lives in both. And Jupiter, all this stuff is stirred up. And if the mush ball things are right, it's stirred up even more. The temperatures are changing. Drop something in there, it's going to float up someplace super cold and then sink down someplace super hot. You know, I'm not claiming to know the answer, but my speculation would be, yeah, Jupiter's not a great place to look for life.
Next question is, does the magnetic field originating at the equator correspond to the Great Red Spot?
No. That was one of our first thoughts. Hey, we've seen this funny looking thing, the Great Blue Spot at the equator, and we see this storm, the Great Red Spot, that's been there for a really long time. Maybe they're somehow related. Maybe this complicated magnetic field is somehow related to the Great Red Spot or to a storm in general. But here's the part that makes that really hard to believe. If you look at the Great Red Spot and you compare it with the magnetic field of Jupiter, the magnetic field that we see at a reasonable distance from Jupiter, so the one we already knew about, rotates really steady like clockwork with a very well-defined period. You can tell that because it gives off radio waves, and the radio waves are a little bit different as seen from different angles in that rotation, and they just go every 10 hours. I forget the exact number, but it's a little less than 10 hours, over and over and over and over and over for years and years, and we know really steady what that period is. The Great Red Spot drifts around the planet. It doesn't rotate at that same period. So what that means is today, whatever magnetic field is underneath the Great Red Spot, wait a couple years, it's a totally different magnetic field underneath the Great Red Spot. That makes it pretty hard to tie it to the magnetic field. Doesn't mean there isn't something else more complicated tying it to the magnetic field or affecting the magnetic field. And we know now that the winds are affecting the magnetic field, and therefore the magnetic field is affecting the winds. So there's something going on, but it's got to be more complicated than just, you know, magnetic field is all twisty and that causes the Great Red Spot, or the Great Red Spot is rotating and that makes a kink in the magnetic field. That's not working. And the Great Blue Spot isn't at the right latitude to be where the Great Red Spot is. Remember, the Great Blue Spot is that one place near the equator where the magnetic field looks quite a bit different. But the red spot is like 20 degrees south of the equator, and the magnetic field spot is right at the equator, and their longitudes only line up, you know, once in a while when the Great Red Spot happens to come around to there.
All right, there are two more questions, and we'll open up to the for open mic on the chats or on the questions. So this next to the last question is, if you had a chance to go back to Jupiter with another spacecraft, what instrument would you change or would you rather have on it?
Yeah, that's a smart question, but it's a really hard one. Knowing what we know now, I think by and large, we brought the right instruments for the questions we were trying to answer. I might have done something different with the orbit, which is hard to do. Or if we had a bunch more money, which, you know, twice as much money as we had, I might have tried to bring a probe also, so that I could drop the probe someplace, you know, further north and get simultaneous radio data plus relatively shallow data from the probe. Other than that, I don't think I would change too much, but maybe I just don't have the imagination to think of. Oh, actually, there's one thing I know for sure I would bring if we could. We asked for that and early on, but it was after we had the proposal approved. We thought of this and said, hey, what if we add this? It would cost, I think it was $20 million more or something. And NASA said no. And that's a dosimeter. Measure the radiation that potentially damages the spacecraft. That's not for our sake. That's for the next mission, for Europa Clipper. So there's now a mission planned to launch in a couple of years to go to Jupiter to orbit relatively far from the planet compared to where we are, but to fly by Europa a zillion times and do all kinds of measurements. It's going to have to go right through the heart of Jupiter's radiation belts to fly by Europa, and it's going to do it a whole bunch of times. And that's territory that we're approaching now and are going to cover in the next year or two. So if I had it all to do over again, I'd put a dosimeter on board, measure all that radiation really accurately so we could give the Europa Clipper folks a hand and tell them, here's what we saw, and here's the damage you're going to need to prevent. So you'll know exactly how much shielding to put on everything and where to fly. We actually thought of that early on, but of course, Europa Clipper wasn't a mission yet. And so we didn't have anywhere near as strong an argument for putting dosimeters on board back then as there is now when it's too late, when Europa Clipper's already, well underway in terms of design and construction and all.
So that actually segues into the next two questions. So I'll sort of combine them. Has Juno been affected in any way by the radiation so far, and what's the expected life mission until radiation destroys electronics?
Okay, so we've had pretty minor radiation effects. We've had a couple of single event upsets. So that's where some charged particle or something from the radiation flips a bit in memory on the computer, and that causes a problem in the thing. Think of it as like when your laptop glitches and you have to turn it off and on again to make it work, right? We've had a few of those, nothing serious, just some of the instruments that recovered just fine. We have, as expected, quite a number of single bit errors in memory. So that's the memory for the spacecraft that's particularly vulnerable, or at least by comparison to the radiation, gets it has some error checking in it, so that if a bit flips in memory that isn't supposed to, we can tell. And if it's only one bit, we can fix it. So there's some redundancy that takes that into account. Every time we fly by Jupiter in those closest approach, we get a few dozen of those. But as I said, we're set up to fix those, so that's not really damage. And much more occasionally, I don't know, think in the neighborhood of once or twice a year, we might get something where we get a multi-bit error, which we can't fix, but we at least know what happened. So then we lose a little bit of data because we have data that's corrupted. Those are all really minor. We expect the solar arrays to start to lose some power, but we're really early in the stage of that. It's hard to say it's even happening, let alone whether it matches the radiation profile we're expecting. If you think back to that picture I showed at the beginning, or maybe I'll share it and show it again. Let me share my screen and back up a bit if I can. Let's see here, this way. This one. Okay, so the radiation belts, the really strongest radiation is here. So at the Jovian equator and a few radii out from the planet. And it gradually fades away as you get further from the planet. And it gradually fades away as you get off of the equator. There's some complexity to that. There's other places and so forth, but that's the big picture. So way out here where we are, we're getting a little bit of radiation when we fly by the planet. The biggest dose we get, because we're moving so much slower, is out here when we cross the equator, but it's still pretty far from Jupiter. As our orbits progress, we're getting closer and closer to Jupiter. So these times where we cross the equator are getting worse and worse. What that means is, if you think about how the mission was designed to survive the orbits we've been in so far, right? And the way the radiation piles up, it gets worse and worse and worse with every orbit. So the radiation from each orbit, more or less, is a little bit worse than the radiation from the orbit before. So we haven't experienced very much damage, but you ain't seen nothing yet, and we're going to. We don't know exactly when it's going to fail. Obviously, we've done our job in designing it. It survived for what it was intended to survive. We think there's enough margin left that it's unlikely, but possible that we might get all the way to the end and have the spacecraft die because it ran out of fuel rather than die because of the radiation. If I personally were going to bet on it, I would bet radiation will get us first, but it's going to be a race between running out of fuel and having radiation damage something irretrievable. Don't really know yet.
Are you going to crash the probe into the planet or just let it stay?
So the original plan was at the end of prime mission, we would crash it into Jupiter. And the reason for that was to avoid contaminating Europa, because Europa might have life. You'd hate 20, 30, 40 years from now to get a spacecraft to Europa, figure out how to land on Europa, figure out how to get through the ice, dig down through the ice, get to that ocean, find life, and then have to say, but I don't know if it's life from Europa or contamination from Juno, right? So we had to make sure we're not going to hit Europa. However, our extended mission, right? There's two things we have going for us that let us get out of destroying the spacecraft. Actually, three. One is it's operating pretty well right now. So a lot of the things that it could have gone wrong didn't go wrong. So that helps. Then it's moving at a hell of a clip. So if it did smack into Europa, there's all kinds of scenarios in which it doesn't penetrate the ice, it just vaporizes the spacecraft, and you don't contaminate anything but the surface of the ice in some spot. Europa's in a high radiation environment, so the radiation would eventually kill that. And if we can show that it would kill that before it penetrates into the ocean, then we still aren't contaminating the ocean. Then there's various failures. If it does fail, what will it hit first? And in most of the scenarios, it would hit Jupiter. And then the key is, once we get past Europa, after those flybys that come really close to Europa that we're going to be controlled, so we don't hit it that way. Once we're past it, then if we suddenly lost control of the spacecraft, it essentially would never hit Europa. The orbit is too close to Jupiter now to hit Europa, and it's far more likely to hit Jupiter as the atmosphere slows the orbit down and changes things. So we basically don't have to worry about it anymore. So we did all the calculations of probabilities of failure rates and all of that stuff, and we're able to show to NASA's satisfaction that we're okay. We satisfy the planetary protection requirements without deorbiting and hitting Jupiter. Now, we have to keep an eye on it and so forth. If there were problems with the spacecraft in some way that made it look iffy and they happened before we fly by Europa, it might be a different story. But our plan now does not include deorbit. It's just run the thing until it finally fails so badly you can't communicate with it.
Okay, I think that takes care of the chat. We'll just open it up to the floor for questions.
Yeah, you mentioned you worked on the near-Earth asteroid project. Did
Just
you
for a
work?
little while, yeah.
Okay, did you work on NEAR?
Yes.
Oh, you did?
Yeah.
So you know Dr. Steve, I forgot his
Pravda.
last name. Huh?
Steve Pravda?
Oh, yeah, that's the name. Oh, so you know him.
Yep.
Okay.
I worked
wondering
with
about
him
that.
for about a year or so. He was kind of running things, and I was just helping out with a couple of software system engineering kind of related stuff.
Okay. I'm surprised we didn't run into one another because I worked to figure out how they were going to store all that massive, and I mean massive amount of data they were collecting.
Yeah, I left the project fairly early.
Okay.
I was on it, I don't remember exactly. I want to say mid to late 90s.
Okay.
Something like that. And we were setting up to try to use an Air Force telescope out in Hawaii to do the tracking.
Okay. So I worked after that period because they had installed that stuff and they were getting a terabytes worth of data a day. It's like, oh. Oh, by the way, the orbit precesses for Juno because of that bulge at Jupiter's equator, correct?
Yeah, technically it's a rotation of the line of Absidies. So it's not that the orbit is tilting from polar to something else or rotating around the planet, rotating about the pole, that orientation. It's rotating so that the long part of the orbit that's far away from Jupiter is moving south, and the near part of the orbit, the perigove, is moving north.
Okay.
Dr. Levin,
Yeah.
are there any lessons learned from the Juno mission that would benefit the Europa Clipper mission?
Sure, we're in good contact with them. In fact, I'm chair of the radiation advisory board for Europa Clipper. So we try hard to, help them with anything we can, and they try to think of stuff that we might be able to tell them. Mostly their biggest concern that they're hoping we can help them with is radiation. And, we're not in the part that they really care about yet, but we're getting close. So we're keeping track of that. But we also, the people who worked on our mission building things move on to other things, and some of them are on Europa Clipper building the next generation of stuff related to what we did, learn things about the propulsion system, solar panels, all of that stuff.
Could the magnetic radiation shielding been improved? Or if you had to do over again, could an improved version of it have benefited Juno?
Want to think about that a little bit. Generally speaking, our shielding has worked really, really well. And the concept that we introduced that is now pretty well accepted, I think Europa Clipper, for example, is doing essentially the same thing, was what we call the vault. We did the best we could to separate out all the most vulnerable electronics and put it in a central titanium vault in the middle of the spacecraft with a lot of shielding around it. So kind of cram all your eggs in one basket and protect the basket really well. I think knowing what we know now, and particularly what we're going to learn over the next few orbits, maybe we would change the thickness of some of those walls in some places and things like that. But I at least don't know of any, major concept that we would do differently. If I had it to do over or whatever.
Thank you.
Okay, Spencer, I think we want to, is there anybody else going to ask any questions? If not, we can go on.
One question.
What is the expected lifetime of the Juno spacecraft, and what is the expected determinative end of life? Is it expendable on fuel or gyro bearings, or what do you think?
So if you ignore the radiation, which is a big if, then we think that the factor that limits the lifetime is running out of fuel. So the orbit that we're in order to stay in an orbit that's both useful and relatively safe, we have to control the altitude of perigove. We don't want to get too close to Jupiter at perigove, and we don't want to be too far. If you're too far, you're out where the rings are, and there could be lots of particles that'll destroy the spacecraft. If you're too close, of course, you're in danger of the atmosphere eating you up. So that takes fuel. Our estimate is we get out to about 2025, perigove 70 something, 75 maybe, before we run out of fuel, depending on exactly what we do between now and then. But of course, I said, if the radiation doesn't kill us, that's a bigger unknown. It's already, everything's already done its job. We've already lived as long as we promised for everything. So the rest is extra. But of course, we want every bit of extra we can get. My guess is the radiation will get us first. I'm optimistic that we'll get into the 60s perijove. So I don't know, 2023, 2024. Kind of doubtful that it'll actually make it all the way to 2025 and perijove 75 or whatever it is, 76, when we run out of fuel. But you never know. And it also, you know, things probably won't fail abruptly. I hope at least you'll start seeing, you know, you lose something and then you lose something else. And then, you know, it gets, it's like me, it starts to get old and decrepit, you know.
Oh, and you can't use the fuel from that main engine that you're no longer using.
Right. Well, we have two ways of controlling the spacecraft. There's the main engine, which is you burn fuel and oxidizer together, get a whole bunch of thrust, and if you do it wrong, you blow things up. Right. That we're never doing again.
Right.
Then there's thrusters, which are basically just burping out a little gas from the fuel and don't use the oxidizer at all. And that's what I mean by running out of fuel. That's what we've been doing now since 2016 to control everything. That had always been the plan for how we would control the orbit. And we didn't do that second main engine burn. So we had a lot more fuel than originally planned for this time in the mission. But you know, we're also trying to make the mission go twice as long. So it's not surprising that sooner or later we're going to run out of that.
Maybe the thing to do at end of mission is test the main engine and go out with a bang.
Yeah.
Oh, yeah.
Well, I think we've crossed that bridge because there's various parts of the main engine that, you know, if you leave it for multiple years without trying to use it, you know, it's not going to be very, you can pretty much count on it not working the way it was intended.
Since we can't watch the explosion, you know, why bother?
Yeah, that's true too. It wouldn't be any fun. All that would happen is the signal would disappear.
Okay. All right. So I'd
like to ask a
closed out. Oh, all right. Last question, then we're gonna move on to the drawing.
Is the upper atmosphere temperature totally dependent from internal processes in Jupiter, or is that also the sun has any bearing on it? And if so, do the poles have a different temperature than the equator?
Yeah, you do get a little sunlight. The poles do have a little bit different temperature than the equator, but actually, depending on what altitude you're talking about in the atmosphere, we don't know exactly how different. There's other things to think about as well, because when you start talking about the upper atmosphere, you got to decide when you stop calling it an atmosphere, right? And the very highest levels where the pressure is really low, the temperatures affected greatly by the aurora and things like that. High energy particles stream down, smack into the upper atmosphere and heat things up to very high temperatures where in the places where the atmosphere is super tenuous. So in general on Jupiter, if you want to know the temperature of the atmosphere, you got to specify the pressure level, and some pressures we know the temperature better than others. And yeah, there's latitude dependence, there's, you know, seasonal dependence, not much of a season for Jupiter, but there's some. There's what's the magnetic field doing, what's the solar wind doing, what are the aurora doing, all kinds of things going on. It's complicated, which makes it fun.
Okay, thank you for the fantastic talk, Steve. I'm glad we got a nice update on that Juno mission. I was originally involved with Galileo, so but anyway, Spencer and Alicia, it is time for the door prizes, what everybody's been waiting for. So Spencer and Alicia, you got the floor.
All right. So I've just I closed out the link for the drawing. So Alicia, you want to take this?
Yeah, I can. Okay, cool. It's almost like midnight here. Yay. No. All right. So we have some amazing prizes. We are giving away Amazon gift cards, flashlights, LAS hats, items from the LAS store, and I think also a laser too tonight. What?
All right, so I've taken the names of for people who registered, and I'm just dropping them into the spreadsheet. Oops, hang on. Let me just try this one more time.
Hopefully Alicia was taking notes on Europa.
What?
Hopefully you were taking notes from him for your Europa mission.
Okay, so the winner is Kelly for the first one.
Kevin Kelly.
Awesome.
Right.
It's great. Thanks.
Okay.
What did he win?
He won an Amazon gift card for
Right.
20.
Which can be converted into a Cupid doll.
What?
Okay. The next one is Jose Aguilar.
Right.
All right.
Jose won a red flashlight.
Right.
Okay.
And see, he's wearing a dark shirt, so it looks like this head floating over downtown LA.
All right. The next winner is Christine.
Christine Soror won a LAS hat. Well, I'm not sure if she's already won one before already. I don't know.
I don't think so.
Well, she says thank you.
Oh, she says I have.
I have, yeah.
Oh, oh gosh, crap. She's won so many times. It's like, oh my, okay.
Give her something else.
What can I do here?
Yes, she's asking about a T-shirt.
T-shirt. I can
Yeah.
give you an LAS store item. Does that count as a T-shirt?
That's a store item.
Yeah.
Okay.
Okay.
Next one is Mark Salzman.
Okay, so I will give Mark Salzman an LAS hat instead. Don't erase it. I need to write it down.
Hey, that's me.
Yeah.
I've already got a hat also.
Are you kidding me?
How about the hat? You know.
Okay, let's see. I will give you an Amazon gift card. Let's do that. That's better.
Awesome.
All right. Let's see. Mike Porras.
What did I win?
Well, obviously you got the LAS hat because I have to do this in a certain order. So I know I haven't given you one yet. So yes, you got an LAS hat. Yes, they're
Awesome.
cool.
Yeah,
I
they're nice
have.
hats. I have one.
I like
yeah.
that.
How many more do we have?
Two, one. Three, I think. Yeah.
Okay. Daryl is the next one.
Yay.
Wow.
Do you need
Daryl
an LAS hat?
No, he won a red flashlight.
All right, I'll take it.
All right,
Okay.
Daryl.
Teresa.
Oh my gosh. Teresa won an LAS hat. Yeah.
Okay. Let's see.
One. No, stop moving. I need to write that down.
Oh, sorry.
Long name.
All right.
Okay, you can go.
Okay. Carol.
Carol Card.
Give her a hat.
No, she doesn't need a hat. That's the last
No.
thing. I got a hat.
Oh my gosh. No, she won a LAS store item actually.
A what?
An LAS store item.
Oh, okay.
Store item.
Right.
She thanks you.
Pavel Lewin.
Oh, we're doing one more?
Did you? I lost track. Was that the last? Was Carol the last one?
Yeah.
Okay, sorry about that.
That's okay.
Well, next time.
You win some, you lose some.
Yep.
Yeah.
Okay.
Back to you, Curtis.
Back to me now. Are we
Yep.
done with the door prizes?
Yep, we're done.
Yep.
Okay, sounds good. Well, we did have a good meeting tonight. I'm glad that Steve was able to give us a nice update on the Juno mission. It was very informative, and I hope probably sometime next year he can give us another update with some more fantastic data from Juno. So, are there any other items we need to cover on tonight's meeting?
Don't forget the elections, guys.
You don't forget the elections.
Yeah.
That's right.
Oh, okay. Well, if there's nothing else to cover on the meeting, I think we can go ahead and adjourn the meeting for tonight. I can
Real quick.
officially, huh?
Okay.
No, all I was saying is Lewis Chilton is definitely holding up hijack for Jack. So
Oh, okay. Well, we can do that after.
I know, my fault.
Why would you hijack this meeting?
Yeah, I thought he was being hijacked or something.
He should have
Oh,
said
well,